say, for instance, reference some memory. The memory the guest is referencing, the addresses the guest could reference there, don't mean anything, don't translate to addresses inside the hypervisor. It's kind of different than if you think about maybe a user mode to kernel mode exploit or issue today, where a user mode process could potentially reference an address in the kernel or get the kernel to reference a user mode address, leading to some vulnerability. We don't have that issue here because we are in separate address spaces. Right. Don't have third-party code in the hypervisor. It's just the code that we've built. It's small. It's one binary. Doesn't change. We're limiting the number of channels from a guest into the hypervisor. And we have that well-defined hypervisor hypercall interface. It's not multiplexed. Really, we kind of want essentially a one interface to one code path separation for the hypercalls, not something complex or multiplexed like an ioctal interface to where one ioctal could represent 50 different functions. We don't allow guest-to-guest communication. And what I mean by that is a guest can't use some virtualization function or backdoor or hypervisor interface to send data to another guest. If a guest wants to talk to a guest, it has to go out through the network interface. We also don't allow shared memory between guests. Right? So for instance, VM bus, where we do have shared memory, is just between a guest and the root. These are separate. We want to reduce and eliminate any potential for guest-to-guest collapse and isolation. And we block guests from touching real hardware I/O. If a guest wants to do something to a network or serial port or anything else like that, it's going to get intercepted. It's going to get passed into the hypervisor and up to the root partition. Right? So the notion of a DMA attack from a guest is mitigated through this approach. So I'm a pretty big fan of mitigation technologies. I recognize that software always has the potential for bugs and for vulnerabilities, and it's really important to put some things in place that, even given a bug, can you make it more difficult for somebody to actually compromise that bug and turn it into an exploit. And so we've built the hypervisor with a whole host of these technologies. The first one, we're using /GS, stack cookies. This means if we happen to have an unchecked stack overflow inside the hypervisor, an attacker can't overwrite the return address. Right? That's one potential attack that's been mitigated at least through that specific path. In addition, we are using hardware no execute. And this means that all of the hypervisor's data pages are marked non-executable. So again, if there happened to be some unchecked overwrite somewhere that allowed a guest to put its, specify some data, some instructions to go inside a hypervisor memory, it can't use that to now actually gain execution inside that space. The hypervisor's code pages are marked read-only in hardware. And again, so if there's an unchecked write someplace that would try to modify some hypervisor code pages, the hardware is going to stop that. Again, trying to shut down these avenues of, given the potential, say that there is a bug someplace, that bug can't be leveraged to actually now gain execution and compromise the hypervisor. Each of these things by themselves isn't super effective, and the combination of them is actually far more interesting. Right. We also have memory guard pages to detect the condition of a stack overflow or a stack overrun or stack underrun. We don't have a really complex exception handling model inside the hypervisor. By and large, actually, there really is no exception handling. If we detect a violation, say, for instance, of the stack cookie got overwritten, the response here at this point is we have to assume that something's gone very bad and that it's time to actually go ahead and just take the machine down gracefully. So this is where a bug check would actually happen. So basically, if we detect the potential for a vulnerability or compromise, the response is bug check the machine and get that data actually logged out. It's a very similar mechanism to what the Windows kernel itself does in a very, essentially far removed, compromised detected situation. It's really not worth advancing. This also means that a lot of the exploits against exception handlers that exist in more complex code, with structured exception handling, just aren't present inside the hypervisor. And finally, the hypervisor's binary image on disk inside the root partition is signed, and it's checked with code integrity and driver signing. We're spending a lot of time, we're putting the hypervisor and the root components through the Microsoft Security Development Lifecycle, the SDL. And this means that we're spending a lot of time doing threat modeling. We're performing static analysis across the hypervisor and the other virtualization stack components to try to find vulnerabilities and flaws. We're performing our own fuzz testing and penetration testing in-house. We've got a dedicated team of test developers who essentially work alongside with the developers and implement tests, including security tests and penetration tests, to try to find as many of these vulnerabilities and issues as we can before the product ships. I mean, essentially, what we're trying to find are ways in which that component there in the sort of the top right, that compromised guest, could potentially try to break out and fix those bugs before we ship. It's a pretty dense slide. This is sort of highlighting the security model that the hypervisor exposes to the root partition. Right? The hypervisor really is only managing a couple resources: memory, CPU, and access to I/O. And as such, the root partition can tell the hypervisor, okay, well, who gets to own what memory? Who gets what CPU when? Who can access which I/O devices? And the hypervisor will enforce those policies. So we can do some things that are kind of interesting. For instance, if a guest has been given some memory and the guest has read-write access to that memory, the hypervisor actually could, under the covers, set that memory to actually only be read-only, or maybe not even have any access rights. So that every time a guest tries to access that memory, generates an intercept, we pass the intercept to the root partition. It's really useful for virtualizing devices and device I/O ranges, but there's I think, some other interesting things that could be leveraged there in the future. We rely on the fact that the hardware guarantees the processor state won't bleed through, as in like readable and writable, between guests. So if we give a processor to one guest, take it away at some point, we give it to another guest, hardware will guarantee that cache registers will be isolated, will be flushed and replaced with the contents for the other guests, so you can't see or modify the previous guest's contents. And that the TLB will be flushed as appropriate where necessary, so that the second guest can't inadvertently map addresses and access memory for the first guest. And that I/O policy says that the hypervisor will enforce whatever I/O policy the root partition says. Some I/O accesses maybe just get dropped on the floor. Essentially, a write to an I/O port might just result in nothing happening, and a read might just always return a page full of Fs or something. And other I/O accesses, the root partition wants to take those intercepts and emulate some device behavior. And finally, the hypercall interface, right? The interface that a guest operating system can call into to sort of become hypervisor aware and do things a little bit more efficiently. There's a collection of interfaces that are essentially exposed to all guests, but only certain guests have privileges to call those hypercalls. So for instance, the root partition is the only partition that can call the create partition hypercall. We don't want a guest OS to be able to create another guest underneath it. We're not supporting any sort of form of nested virtualization here in Windows Server virtualization, at least not in this version. So managing virtual machines and saying who can create them and start and stop them often falls in through departmental roles. Right? So you might want to have a finance department be able to create some virtual machines, and an engineering department manage and create another set of virtual machines, but not allow them to actually manage or manipulate each other's virtual machines. So in order to implement this, we're using something called Authorization Manager, AZ-Man. AZ-Man was introduced in Server 2003. It lets you just have fine-grained, role-based access control to say what groups of people can do things in certain operations. And so for us, it's things like starting, stopping, configuring a VM, saying what virtual machine has access to what virtual devices. And what that allows us to do is give somebody the ability to be an administrator for a collection of virtual machines without actually having to be physical local administrator on the server itself. Let's skip ahead and talk a little bit about time virtualization. I wanted to put this in here just to sort of give some insight into some of the design decisions or trade-offs that we make pretty regularly on building the hypervisor. Time's a really interesting one because virtual machines are really affected in really unique ways by time, in a way that a physical machine, an OS running on a separate piece of physical hardware, would never really see. And so we recognize that there's really kind of three categories of time. The first major one is calendar time, stuff that you see off a clock. Right? Virtual machines get access to calendar time through an emulated device, an emulated real-time clock. But then there's actually sort of lower level, like machine time. Right? Things like, how many processor cycles have actually clicked by since I've last executed. And we provide to virtual machines a virtual APIC. This is an aperiodic programmable interface timer that a guest can program to get interrupts sent to it. We also provide a synthetic interrupt controller that provides a little bit more robust interrupts that a guest can program to get certain time events to come back to it. Right? An OS normally on real hardware does this to essentially wake up or reschedule certain threads in the OS to do activity or respond to interrupts that come in from hardware. We have to reflect these things back into a guest itself. And then the last notion of time is one that's internal to the hypervisor, scheduling time. Basically, how long has a virtual machine been able to run on a processor? Because we have to share processors amongst guests. Every once in a while, we'll have to take a processor away from one virtual machine and give it to another. All right, so that said, one of the things that we had to deal with, grapple with, is how do we handle reads from the high-performance timestamp counter, right? This is something in the CPU that ticks by every clock cycle. So if a virtual machine were to do a read from the timestamp counter, do an instruction, and do a read again, well, in real hardware, you'd expect a very small amount of time to elapse in between. In a virtual machine, though, you can actually have a huge jump of time that every once in a while can happen if we take that processor away to give and schedule to another virtual machine, and eventually give it back to him. You can also have a huge jump in time if the instruction that's done in between the reads of the timestamp counter generates an intercept, right? Maybe one of those I/O operations that I mentioned earlier. So, it's kind of coming down to, well, what are we going to do for a guest if it sees the timestamp counter, jumping around in very strange ways? Do we want to stop that? Do we want to make the timestamp counter look like it's always just normally incrementing and not having these big jumps? Because the hardware gives us that ability. You can set in the virtual machine control structure the ability to essentially roll back the timestamp counter, set an offset, so that the guest won't see the time that's elapsed, the processor was taken away from it and given back. So we kind of have, one camp or one way of thinking around, well, we could just allow the timestamp counter to go ahead and jump ahead, right? Let it advance naturally. This can actually happen on real hardware. If, for instance, system management mode were to kick in while an operating system were running. But one of the big problems is that because every once in a while we'll shuffle processors around, we actually might take a physical processor away from a guest and then give a different physical processor back to the guest. And the two processors may have drifted TSCs, right, that very different times elapsed on the timestamp counters. The guest actually has a risk of actually seeing timestamp counter jumping backwards in time. That's not something you'd ever really see on real hardware. So likewise, we had the idea of, well, we can always modify it and make it appear like it's never changed. So essentially, when the processor is taken away from the guest, record where the timestamp counter was,